emailed in comments that we just heard from Mr. Rathie. So, Carrie, welcome.
And I'd just like to note to everybody what a pleasure it is to have Kerry here again, because I've known him forever. Ever since he was little, well, actually, I've known Tom for a long time too, but ever since they were wet behind the ears, because we used to be able to bring undergraduate student tour groups down here, and the people here at the plant did such a fantastic job of showing them around, getting them in the simulator, and mentoring them. So it's a real pleasure, Kerry, to have been able to watch you all this time and all of the great work that you've been doing. So
thank you very much, Dr. Peterson, and it has been a pleasure knowing you all the time. And I have to say that although I show my gray and I'm aging out, I'm still trying to find your secret of staying as youthful as you look.
Actually,
I work hard at it.
I give all the credit to my wife, who's here with us.
Did he say wet behind the ears? Did he say that?
He was, believe it or not, he was like really young and stuff.
Well, I want to say that I used to be wet behind the ears. Now I have hearing aids behind the ears.
Now I have a little bit of moss back there. Okay.
Welcome.
Thank you very much. I really appreciate the opportunity here, Mr. Chairman and members of the committee and the esteemed consultants. So I'm here today to give an update on a couple of things. I'll do two presentations. The first presentation is an update on the status of our Unit 2 main generator. And the second presentation will be general state of the plant. The second presentation will probably go a lot faster as the plant has been operating very, very well since we last got together. So I'll start with the main generator. So just for the public that's viewing, just so you're aware, as Tom mentioned, I'm the station director, so I'm not a generator technical expert, but I know enough to be able to be a little bit dangerous about the subject. So we'll start off here. So one of the things that I want to mention, just so that everyone is on the same page with respect to the Unit 2 main generator, is that the Unit 2 currently is safely operating and producing electricity for our customers. So the unit is up, it is running very, very well, and I'll dive into a little bit more details about that in a minute. The main generator is located on the non-nuclear side of the plant. So outages were focused on restoring reliable electric generation. I want to be very clear about that. You could find a generator like the one that we have on a very large conventional power plant that is not fueled by nuclear power. So that's where a lot of our activities were focused, is restoring that back to a situation where it will be reliable and will not create any issues for us and our customers. It is not a nuclear safety issue, as I mentioned, and no impact to the health and safety of the employees and the public as we went through the activities to address it. Although it was a significant amount of work, and I'll talk a little bit about the specifics. So I'm going to give a quick summary here. That's, the whole tell them what you're going to tell them and then tell them what you told them after you tell them. So the summary here is the Unit 2 main generator has been online for approximately 2 months. So since the last time that we made the final corrections on the generator, we've brought it back up following our refueling outage, and it has been operating well. Significant additional instrumentation and enhanced monitoring has been installed in the generator. So with all of the things that were going on with that generator, we felt the need to go well beyond what is normally installed to be able to monitor the generator. And so we connected a lot of instrumentation. And I'll point some of that out so that folks will get an opportunity to see what that looks like. We are in the midst of a root cause evaluation to identify any additional corrective actions that we might need to take. When we go through the root cause process on any type of issue, we identify what the issue is. We bring the right people together to be able to identify what the gaps are and what the drivers are to those gaps. And then we take immediate corrective actions. We have to do that to restore the systems to an operational status. And then that's usually followed on with additional root cause that goes into in-depth issues, such as maybe there might be organizational, or maybe there might be other type of issues that we use a root cause process to be able to scrub. That root cause is not completed yet, and so we continue with that effort. As part of this effort to be able to help us identify immediate actions that we needed to take and to help us with the root cause, we leveraged a number of vendors the main vendor of the machine, as well as some industry experts in vibration analysis and structural analysis to help us with this. So through all of this, we executed as far as the staff when we were navigating the units around to address this. The real good part of it is that our operations staff and our maintenance chemistry, there's a number of folks that are involved with this, they operated pretty much flawlessly and executed the shutdowns and the restarts of the units, as well as being able to clear the generator and restore it back to service on each one of those issues. So I'm going to hit this slide fairly quickly. It's just a timeline slide just to put us all on the same page. So what I'll do here is that first bar up there just notes that our generator was coming at the original generator was on Unit 2, was pretty much at its end of life and a little bit past the end of its life. So that facilitated us the issue that we had to resolve. And so the way that we resolved that was through a rewind and rebuild. And we used the original manufacturer to do that for us. And that occurred in September of 2019. Then we began to see some issues associated with the rewind, and they didn't show up in a significant way until July of 2020. And at that, we started to see some hydrogen leakage that was exhibiting itself from the unit, and then from there we shut the unit down to go after that. And I'm going to hit each one of these in quite some detail. Okay. Then from there, we made some repairs, and then we found some additional issues with it as we moved all the way through the beginning of this year.
Kerry, actually, I've been curious. What's the logic behind the numbering scheme going from R to Y to Z to G to H?
Yeah, so what we do is the R is refueling, and so that's a standard.
That one I know.
Yeah, and then from there, we pick a letter, and I don't know the exact reason why we start at the Y's and the Z's, but our outage management team likes to make sure that they're designated, and then they just pick one, and we just.
So this is kind of like naming hurricanes, then.
It is. I do know that the G was selected because of generator.
Okay.
But the X's and the Y's, your guess are probably about as good as mine. So I'll talk about the July outage that we had. So the July outage was the very first time that the issues with the Unit 2 generator showed up in a significant way, in that it showed up with a crack that was on the stator cooling water header. Now, for those who are watching and not as familiar with the generator, that generator is extremely large, and it is cooled by hydrogen gas inside of the generator. And inside is a big rotating element called the rotor, and then the stationary part is the stator. And then what allows the heat to come out of the hydrogen, so you got to remove that heat from the hydrogen, is a stator cooling water system, which basically is a closed-loop water cooling system. And that system then takes that heat out and goes through a heat exchanger that's external to the generator. So anyway,
Kerry, I think there's a couple of additional important points. The stator cooling water also directly cools the stator elements, correct?
That is correct.
And then the hydrogen runs at higher pressure than the cooling water, so that if there is a leak, you do not leak water into the generator.
That is correct, because thank you for pointing that out. So the generator is, of course, electrical inside, so you don't want water in the generator. So that hydrogen gas at the higher pressure, should it leak, as you said, it will go inside the static cooling water system, and that allows us to be able to see if there's hydrogen leaking into that system through a vent
Correct.
point.
And then the other thing is that the hydrogen leaking into the water creates bubbles and stuff, but does it substantively affect the capability of the water to actually provide cooling to these structures? Or is it, my understanding is it shouldn't really impact the cooling capability, but you can't sit there with it leaking for long periods of time.
That's correct. So it does not impact the ability for the static cooling water to be able to cool the system. And so you want to monitor, because you don't want a tremendous amount of hydrogen, but if it does, we monitor that on event points so that we can tell if there's...
Correct, because there's a you have the capability to get gas out of the loop as you would on any of your water cooling systems.
That is correct.
And you can do that online, correct?
That is correct, and it is designed that way, and that's something that the operators monitor so that we can pick it up if it becomes an issue.
And then where do you vent that gas that you collect from that system?
That's vented out a vent without having a drawing. It's a little hard to describe.
It goes outdoors, right?
It goes outdoors. That's
okay,
correct.
good.
That's correct.
So in that case, then this type of problem does not fundamentally challenge the ability of the cooling water system to provide cooling to the generator.
It does not.
Correct. Okay. And it also, because the hydrogen vents outdoors, doesn't create a immediate hazard of mixing and explosions or that sort of thing, right?
That's correct, because the hydrogen gas, as you're aware, is extremely small in comparison to the environment.
Well,
Good. Okay.
at high,
I think those are important points. Thank
at
you.
high enough concentrations to be a problem, but it's a very, very low concentrations compared to any problem.
That is correct. So the way that this showed up at the first time was a crack on that static cooling water. It's a connection point that connects to that header, and I'm going to use the little pointer here. So here is the static cooling water header, the silver thing, and we're going to see that a couple of times here. So I want to make that pretty clear for folks. And then here is a connection here where water comes into a static cooling water header. Okay. Now, when the water comes in through this header, this gives a little bit more close up to that connection. If you notice, there's sort of a box here, and it's just sort of the design that the vendor put in place initially. And so the water comes through, it comes into this location, and then goes into the system there. So we saw an issue with a crack right around this location right over here.
And there's a weld in that location also?
And there's a weld in that location, exactly.
Not the best place to put a weld.
Huh?
Not the best place to put a weld.
Not the best place to put a weld. That's correct. That's correct. As a matter of fact, the configuration that we have here was not as we we work with the vendor and the vendor analyzed it. They came up with a much better design for this whole connection point right
Correct.
here.
Every single time you do that sort of miter weld, it's going to crack and leak.
Yeah, and I'll show a picture that shows the stresses at this particular area here that made it susceptible to that.
Oh, yeah.
So with that, we repaired and did a replacement of that weld because the initial analysis was looking at this particular location and recognized that it wasn't the ideal situation, and it resulted in vulnerability. So that was the initial issue that we had with the generator. And then if we move over to the next situation. So we made that repair. And that repair, of course, now as you zoom in at a farther view around in this location over here, we also, we got back up, we started running. We ran until October. And then in October, we experienced another hydrogen leak that was detected. From that, we brought the unit back down, went into the generator and inspected. And we noted that there was another crack in that static cooling water parallel ring. And it was also a fillet weld. This is just a really close look, and you can see at a high magnification that when we talk about a crack, it is very small, but hydrogen is such a small element, being the smallest element, that it allows it to come out of that micro crack, if you will.
Could you give a sort of a sense of scale? What's the diameter of the internals there?
This diameter here is roughly around, I'm going to say maybe about 2 to 3 inches, maybe.
Okay, and then the overall machine?
The overall machine is
Looking-
this is many feet. We'll get an opportunity.
walk through
As a matter of fact, you can walk through it. If you could stand right here, and there's many people as it was being constructed, took pictures where you could just stand. Literally, someone who's 6 feet could stand in this area right here. So that gives you a good feel for the size of this machine. It's very large, and like I said, with the rotor that spins around inside, it's a very dynamic sort of a situation that you have with this machine. So out of that, we worked with the vendor, and at that point in time, we brought in our experts to help us from a structural integrity standpoint and a vibration standpoint. And what we did at that point in time is we capped and redesigned the support frames for that and the loading frames. So basically, try to load and re-support it. So this is the box that I was describing here that we saw just a little while ago in the specific weld location here. And this has occurred in the December timeframe where we got that additional crack. And then what we did is we kicked off a finite element analysis, which is basically a extremely technical way of modeling the stresses that are at any location within a fixed amount of material. And it requires a lot of high-powered computation, and that could tell us where we are seeing the biggest stresses. And so you can see here the red indicates the highest level of stress, all the way down to the blue, which is the lowest level of stress. And so out of that, we were able to confirm that indeed those are high levels of stress points.
And there's a weld in a stress concentration location.
Yes, and there's a weld in the stress concentration location. So as we work with the vendor, what the vendor then came up with was a completely different design for that. And the design was such to remove that stress. So basically remove that blocks completely, and then pour it in with a standard T, which experiences less stress.
Yeah, and no weld in the high stress.
Yeah, no weld in the high stress.
You should never put welds in high stress locations.
That is very true. So what you see on this next page here, and I'm going to point it out, you saw the box before, but now you see it's a smooth flow of water straight into this T. So the box is removed, and now you just got a smooth flow, which eliminates that stress point, and it goes into that static cooling water ring. So that transition box was removed and eliminated. Now, at the same time, as we were working with our experts, we knew that there was a vibration element that was driving this as well. And so there was a modeling that was performed on the entire generator frame. So here you can see a couple of individuals standing or sitting back about 20 feet from the generator. So you can see how large it is, and the whole generator is not in this picture. You can see the individual standing. That gives you a scale. And so it's a pretty significant machine. And the vibration analysis for the that was done on this, the modeling was quite sophisticated, probably one of the best in the industry, because it actually showed exactly how that frame moves as you got the rotating element inside with the magnetic forces being applied. And so you could actually see on that model, the way the frame was actually, contorting. And that was very significant because that, and you can write it, I mean, that's a university paper in and of itself. That allowed us to be able to see what effects the frame would be having on the whole system. And so with that, what the folks came up with through the analysis was that, like you do when you balance in a very simplistic way, when you take your tires from your car put them on the machine when they balance your tires. They spin them around on the machine, and then they analyze it, and then they tell you, I need to put a weight here, and I need to put a weight here to basically dampen that vibration. So try doing that with a super large machine with the internal spinning, the externals not spinning. Very impressive work. The team came up with locations where we had to put counterweights to balance the machine. So just like you would on your car when you put the balance weight on your tire, you don't say, oh, my tire's now all broken because I had to put a counterweight on it. No, that helps to dampen the machine. So we added these counterweights, and there are about 6 of them. And this is in their initial stages when we were putting them in just to make sure that we could get it right, because there's a little bit of iteration. So there are 6 of them, 1 here, 1 here, and 1 here, and then there's 3 on the other side of the generator. And that allowed that motion of the frame to move away from what we call a natural frequency of resonance, which is a higher level of vibration. So the thing that I'll point out also is, so you see the individuals there, and you see all the equipment that they have that they use to monitor the vibrations in the generator and outside of the generator. So we ended up installing a tremendous number of accelerometers, which are basically things that measure vibration both inside of the machine and external to the machine. You can see some of the wires going over to various locations, either into the machine or external to the machine. And there's one running up the side over here, and there's a number of them everywhere. So it's instrumented in a way that is significantly greater than any machine of its type. And that allows us to be able to see, how the modifications created an effect on the generator. Well, the good story of it is after we did that, we did see a reduction in the vibrations of the unit, and we got the frame and we got the stator down into a very good range of performance.
Now, Mr. Harbor, may I ask for some context here?
Sure.
I used to think we have over 2,000 reactor years of operating experience of main generator.
Mm-hmm.
We're 104 nuclear power plants, 30, 40 years of total, years of operation, and not even globally. But it appears to me that these sequentially happening failure seems to be something new. You mentioned modeling, you mentioned, making numerous adjustments here and there. How did that happen? It's some of these failures are totally unanticipated. Is it something new? You're buying a new machine?
Yeah, this particular failure, so it was definitely unanticipated. A lot of the machines that have been out in the nuclear fleet have been there for a while. Some have done replacements of whole stators where the whole unit has been removed. That happened at the Arkansas Nuclear 1 plant. Unfortunately, because of the loading of that particular one and the failure of the crane, it crashed down through the floor, and unfortunately there was a fatality. There was a significant amount of damage. So as we analyzed, we didn't think that was the best way to go due to our seismic configurations and the vulnerabilities of that. So we had a stator replacement sort of in place, if you will.
But the question is, hindsight is always 20/20.
Mm-hmm.
But knowing what you know now, if at the very beginning, if you just replace this old equipment with an identical replica, just replace it, you would not have these issues.
We don't know.
We don't. Yeah, we're not.
Right.
Yeah, we don't know that because what we did, the internals, it really was pretty much a like for like. They just pulled out the old and put in the new.
Yeah,
So it was for all intents and purposes meant to be a like for like replacement.
Let me try to comment.
Your initial aim is to procure something better than what you have, right? In that context, that something better turned out to be difficult to manage.
Well, wait.
no.
I have a different interpretation. It might be slightly different and better, but the aim was to make like for like.
Exactly.
And in fact, my explanation is that when you manufacture these great big things, they're not all identical.
Mm-hmm.
There's some variability. And this particular thing had variability that was unfortunately caused these failures rather than the more modest variability that turns out to just be normal.
Yeah, that's correct.
That's my interpretation of what it was, rather than it was a brand new thing, you branched out, nobody knew, and you got bit.
Yeah, that's correct.
I kind of don't think it's that latter.
Yeah,
Well,
this was for all intents and purposes a like-for-like replacement. So the core was removed out, and a new core was moved into the same machine.
But the new core is different than the one that you replaced.
We
The
now
new
know it
thing-
is.
Right. Whatever you
The
brought in-
vibration characteristics are, but the materials and everything else associated is the same.
But the dynamic performance of
Yeah.
it was really different, right? The new stuff you brought in.
That's correct. So yeah, and so it's just a matter. Like I said, it's not like they were meant to be like an upgrade or anything like that. It was pretty much just pulling out the old core, putting a new one in place, but that one just had vibration characteristics that are different. Sometimes we might replace like a pump motor, and it might be the same motor, but it comes down and it sits down in the same location, but the vibration characteristics are slightly different on that. And so we see that even on a smaller scale as well.
Yeah, and whatever you call slightly different is almost always well within specification. You're okay. This happened to be more than slightly.
That is correct.
Is that a way of just trying to explain
that
it
is
to the layman?
That's exactly it. It was outside of the specifications in terms of vibration.
I've
Than what we would expect.
subsequently spent a fair amount of time, for various reasons, looking at this question of these complex mechanical systems and vibration, because it turns out to be really important in a wide variety of applications. And it's commonplace. You start it up, run it at low speed, you find out what's happening, and then you go in and you add weights, you tune, you stiffen in various different places, and you tune it up to get the good performance. This one took a long time to get to that state, but it's very common that with things you have to come in, these complex mechanical systems, and make modifications and essentially get things balanced up to the point where they don't vibrate badly.
Yeah, that is correct. And I'll use another example of that. So our plant used to be designed with 5 emergency diesel generators. They're pretty large machines. They're about, they're probably about, yeah, locomotive engines. And we installed a 6th one back in the 90s to give us greater levels of redundancy. And and it was the exact same machine as the other ones, pretty much down to the letter. We put that one in, and I know this one very well because I was a project manager on it. We got it all put in place, based and set, started the machine. Machine works great. We did a lot of testing, but it shook more than the other machines.
Yep.
And it took us a lot of iterations to get that to the point where we could bring that vibration down. So starting it up, loading it, shifting it, and going through iterations of changing the base a little bit, making sure the counterweights were okay before we finally got it to where it was within the specifications that we required. So it's a little bit of a science and an art as well.
It's
Right.
very common. It's very common.
Well, now, how common is common? I thought this is pretty unique experience that you had gone through of this sequential fit.
It's essentially all mechanical systems like this end up needing to get tuned up. And generally, once you get to the point where you've built a whole bunch of them, you get everything balanced correctly to start with. But otherwise, you'll spend a lot of time getting these things tuned up because of all the complex ways.
But anybody else out there, any licensee out there, gone through this type of extensive, I would say, modification, experimentation, contractor support, modeling? I mean, it's just one of its kind of episode.
So I would say no. So another member of our STARS LLC Alliance, the Callaway Nuclear Power Plant, so they also had a generator stator overhaul along with the rotor and so on, and they have experienced some tremendous issues as well. And they have been down for I don't know, maybe about 150 or more days while they're working through having the vendor go back, address it as well. So I would say the thing that is uncommon is there's not a lot of heavy, and I will call this particular job heavy construction that you would see in addressing these type of issues with the community.
So it took Callaway about 120 days
at least
to fix the issue.
Yeah, they're still not back up yet. So they're slated to come back up in the latter part of July.
So
How many days is taken this facility?
For our facility, we were down for about 160, 170 days, up and down.
Well, but I'll go back to the characterization I gave you just a few minutes ago. There's always variability in these things,
Yes.
and you hope and expect that the variability will be well within whatever specifications will give you trouble, and this one was outside, and that's some sort of bad luck because obviously whoever's doing it is trying the best they can to stay as best they can within the specifications, but the variability is just an unfortunate piece of bad luck, I think.
Yeah,
I'm not arguing about blame here. Obviously, in the end, you're going to get to the bottom of what it was, and you can talk about blame. But I'm just watching the process.
Yeah, and right now we're going through the whole root cause, so I'm not, at the point where we're going to point blame or so on. We're just going to try to track down, what the issue was and make sure that it's completely and totally resolved. So just getting to the counterweights, those were very helpful for us, and that allowed us to be able to really dampen the vibrations significantly. So we brought the unit back up after that, and of course, as we do, we check it and we monitor the vibrations, both internal and external to the machine, to make sure that we have addressed all the issues. And by and large, the frame vibrations had decreased significantly, as well as the static cooling water header. And I'll point to that again just to refresh us. That's where we were experiencing some issues there. That had also, the vibration in that had also come to an acceptable level for us. Unfortunately, we had one outstanding area that had higher vibrations than what we would have liked, and that was this area. So right inside of this is the parallel ring. And these conductors here, we saw that the parallel ring, when we got to 80% power, that it was above what we would have anticipated. So as we got to that, we had some already predefined criteria that we did not plan to cross. It was well before it became an issue. So we did end up with a small hydrogen leak. It was actually, the hydrogen leak was well below where we would actually be required to take action. But given that we had experienced it, that leak, and we know that we were heading toward our outage, refueling outage, we decided to reduce the load on the unit, take it offline, and commence our refueling outage. When we got into the refueling outage, which is where we were going to go in and do a full replacement of the ring, and the reason we were going to do a full replacement is because it had been shaking for a while. There might have been other areas that have created cracks that we may not be able to have seen. We went into the machine, and then we identified that there was a crack, and you'll get to see this in more detail here, in the parallel ring. It was a very small crack, and we'll see that one. It's like right about here. So as part of the work that was done, the team removed the parallel ring, replaced the parallel ring, and then we went after the crack that was in this location here. Now, the other thing that I'll point out, since we got a good picture here, is if you notice these conductors here, these parallel ring conductors, if you see these, you can see these, I'm just going to call them supports. That's probably the best way to characterize it. That stiffens all of that so that things don't shake around. And that's going to be important as I move into the repairs that we did to mitigate the problem. So we learned from additional analysis from our vendors and our structural assisting companies, that we needed to add additional supports on that parallel ring. And so you can see that we installed 37 new braces and blocks, and those are these items here. And the reason they look plastic is because they're you got electricity flowing around here, so they have to be non-conductive. So we installed about 37 of those to stiffen that parallel ring up, and that resolved the conditions for us and brought that last part of the machine back into spec. Now, this picture shows the location of that crack on the parallel ring. It shows just sort of a high level. You can see everything's all wrapped up here. When you remove the wrapping off of it, you get to the actual parallel ring itself. That's after you chip away all of this, because this material is actually not a tape. It's really like when they're done, it's almost like a concrete. You got to kind of chip it away. And when that's all done, then you get down and you can see just this little hairline crack right here under magnification. So what we did to make sure there wasn't an extent of condition is we did radiography in various locations within the parallel ring just to see if there was anything else that would be showing up as a flaw or any other issues that could result in a crack. We did not identify that, reviewed that with the vendor and the structural folks, and then from there we were able to exact the repair on that, and that allowed us to complete all of the work for that unit.
Were you able to do the radiography without removing that coating type of material? Or did you have to take that off? Or what you were doing radiography in locations where you didn't have, I'm not even sure that it's interesting, whatever that material is that's on the outside of the pipe.
I don't recall if we had to remove it. I don't think we did, but I'll phone a friend here and see if Tom is aware. Tom, do you recall if we had to remove?
It looks pretty low density, so I think you can radiograph through it.
I think we did. I'm fairly certain, but I can't say for sure.
Yeah, because you can shoot through a fair amount of other stuff.
You can.
You'll get a good radiograph.
Yes, because it's high energy, as you're aware.
Yeah.
So I'm fairly certain. But we can follow up with that on
That's
a fact
good because
finding.
not having to chip that stuff away
Yes.
is a good thing.
Yeah, because it'll create all sorts of other issues with dust in the machine and so on that can become an issue.
Yeah.
I'm 99% sure that we didn't. But to be that 100, we'll do a follow-up when you on your next visit. So we made that repair, sent that back to the lab, had them analyze it, and once we made the repair and we had done the additional supports for the parallel ring, then of course we validate all of the impact on vibration using a bump test. And you bump it, and then you see where the frequencies go, and that tells you if you're there. But it's never as good as actually running the machine, because you can't get 100% until the machine is up and running. That's that whole science versus the art part of it. You can use the science to tell you that you're right there, but you really don't know 100% until the machine is up and experiencing all of the dynamic forces it's under.
How do you bump it? Using a soft pedal?
That's a good question. It's a machine, and I actually got a chance to see this machine that they connect up to the machine, and it exerts some sort of force on it, and then they can measure and that means something to these vibration experts, but and they can tell what impact it has on the vibration.
It's not as crude as that, but I want you to imagine this is just being blunt. You hit it with a hammer and it rings.
Yes.
And if you find something, you got to fix it. But if you don't find something, you're not in the clear yet. You still got to run the machine.
That is correct.
So this is a way of kind of getting some of the things you might find that are resonances or something that's out of whack that you can observe this way, and then later on you really got to run the machine to pin it all down.
Yes, you nailed it. As a matter of fact, that bump test, I have seen that done on smaller pieces of equipment.
Yes, in
and
fact,
it is a hammer, like a hammer.
Yeah, I have seen it. I have seen it on a rotary pump where the thing is slightly out of line. Mm-hmm. You're right, like this, and then you repair those, and then you hope that when you run the whole thing, it'll be okay. And sometimes it isn't. There's something that this bump test you didn't excite it in the right frequency range or something.
And on the larger machine, it's just a machine that does it, because
the whole
it's
big
too
thing.
large for the hammer.
Yeah.
So, so it's been quite a journey working on the machine and getting it to where it is now. So as we sit now, the vibration on the generator prior to the repairs was, where it was. That's like the condition of the old generator stator. It was, we call that our baseline. That way we knew it was running fine then, and then we compare everything to the baseline. And so the vibration levels that started in November were higher than the baseline, which is why we were experiencing some of those cracks. Our vibration was close to the baseline with the addition of the counterweights. When we put the counterweights on, that shifted the frame, got it back in, and we were close to that baseline until we got to higher power levels. And then we noted that there was issues associated with the parallel ring. By addressing the parallel ring with the additional supports that we put in place, the blocks, that has now, if I were to show you a graph, it basically the machine is now vibrating at a level below the baseline, so it's the best it's ever been. So it's right now we continue to be, I'm going to say, cautious. So we have the instrument, the machine still instrumented in a way that other machines are not, while we just monitor it on a shiftly basis. And there's something that comes out, it's 24/7, continuous monitoring, just to make sure, from all of us who have been through this, we can begin to feel more comfortable with what we've seen. But right now, everything is looking pretty good, and the machine is operating well below the baseline and well within normal operating parameters. So that's pretty much where we're at with it. And at this point in time, as I mentioned before, the team continues to work through the cause evaluation, and we have the vendor heavily involved with that, as well as the other companies that have been assisting us with this.
So right now you're reasonably confident that the solution is adequate and don't anticipate any problem for the system.
That is correct. We are reasonably confident, and that's a good way of putting it, because the way, like I said before, we there's a whole sophisticated way that you go around and analyze this with fault trees and so on that helps you get to your initial actions that you have to take, but then you finish it up with the rest of the analysis. And until that's done, we're not 100%, but we've got very good, engineering technical reasons that everything is operating well, and will continue to do so. And that's all I have. Penny, any other questions that you have?
Before you came, we had a discussion about this earlier in the day. It was in the context of one of our fact-finding reports. And I expressed my personal view, which you've reinforced, which is that we, the committee, don't know, because you don't know, and nobody yet knows what the root cause is that caused this headache. But we concluded, or I shouldn't say, at least I, Bob Budnitz, concluded, and I think the committee generally will concur that they concluded that once this unfortunate thing unfolded, we thought that the plant's response was competent and well done, given the initiating event which you unfortunately had to go through. So we conclude that before you got here. I'll say it again. It's in one of our fact-finding reports, and I think everything you've said here reinforces that conclusion that we had articulated, I don't know, a few hours ago.
However, Mr. Harbor, I do want to share with you some responses from members of the public is slightly different than what from what Dr. Budnitz has indicated.
Oh, fair enough.
I thought, with Mr. MacArthur's, as a team member, our fact-finding report had stated factually that in your endeavor to find a solution, your responses had been adequate, quote unquote. But one member of the public had provided us the input today is saying that is laudatory. Ooh, that has a different context, right? So I've taken notice, because the tone of our committee's report, it's also important other than its merits, right? So the committee, in my humble opinion, is an independent safety committee, and we are neutral, we really neutral. and our charter is on safety review, right? So that's some of the input I want to share with you.
Well, I want to comment on that. I believe that I entered this evaluation neutral, and I came out of it neutral. But where praise is due, it will be expressed. And Bob Budnitz has expressed praise for the way this was handled on the response side, holding judgment yet about what happened that got us into it, got you into it, okay? The word laudatory is a word I proudly endorse and grasp as correctly capturing my own evaluation.
Thank you, Dr. Budnitz.
On the other hand, maybe not everybody says that, but I said it, and I stand behind it. Good for you.
Yeah, thank you very much. There's been a tremendous amount of effort, and my hat's off to the technical team. This is unlike anything that I'm going to say in comparison to the technical challenges that we've had at the station in the past. We all, from a leadership perspective, agree that this is the largest technical challenge we have had, and it's taken a lot of effort and a lot of expertise to be able to get us to where we are.
Yeah, I have one more question. We talked about this morning that there was one additional outage, and it's what I would call semi-related, and that was with the swapping of the hoses on the Stadler cooling water, which is a part of the story, but not a part of the story. But just for completeness, because I reported on it this morning, and we haven't heard anybody from PG&E talk about it, could you give a brief summary of that event and your perspective on it?
Yeah, I can. Thank you very much for that. So this one, this was at the very end after we had already made the modifications and we had returned to power from for Unit 2 coming out of the refueling outage. And when we got up to about 30% power or so, we were constantly monitoring the machine, and we noticed that one of the thermocouples was deviating from the others. Actually, probably two of them that were deviating in temperature from the others. And so given that, we were watching this thing like a hawk, we stopped the power ascension and then got the technical experts involved in analyzing the issue. And one of the engineers, which was, I believe it was one of our engineers, the system engineer for the generator, had identified that this was indicative of some sort of lack of cooling type of situation. So we got the vendor involved with it, and as they looked at their information, they concurred that they think that there might be an issue with the hose connections. Now, the vendor does a test to verify that the hoses are connected. They do a type of a flow test that they use, and that flow test ideally, they felt would let them know if everything was connected correctly or not. And what we identified as we shut the unit back down, we opened up, went inside, and we did indeed identify two hoses that were not connected properly. And then from there, we met with the vendor. We restored the hoses to the correct configuration after evaluating and looking at their tests. We did verifications to make sure that those hoses were connected as well as the other ones, that they were connected okay. And the vendor is taking a series of actions around how they verify that. So there will be more to follow with that as well.
Thank you.
And I should just say this, it resulted in no damage to the machine because we were monitoring it and we just saw it before there was any
Thank you.
excess loading on the machine.
Thank you.
Shall we entertain public comments on Mr. Hart? Members of the public, please come forward to the podium.
Jane Swanson, San Luis Obispo Mothers for Peace. I have two questions. One, I'm interested to know if PG&E or this committee considered it a dangerous situation to have Unit 2 ramped up and down repeatedly. My understanding is that's the most hazardous time for a nuclear plant, when it's on the way up or on the way down.
Yeah, that's an easy answer. You don't want to scram it in anger. It's like putting the brakes on in a car when you're going fast. But a slow, orderly shutdown, while still hazardous compared to operation, is much less troublesome. And they had the time to do a slow, orderly shutdown in each of these cases, so it was not the trouble that we were largely very much concerned about. If you have to, we call it scram the reactor on all of a sudden. Okay. Anybody else have a comment about that? I think that's sort of the general evaluation.
It is not ideal, but they had to do it. They had to do it, right?
Okay.
If they don't have to do it, they'd rather not.
And they're well trained and they know how to do that and they do it all the time.
So that answers my question, the combination of it's not ideal, but they could do it gradually.
But they had to do it.
Yeah.
Right? They
You're
had to do it.
always, if it's running smoothly, the safest configuration is just sit there and run.
Okay, thank you. And my second question is.
Let me add to that, if I
Oh.
may.
Go ahead.
This is true. Let me say the machine is designed to start up and shut down, hopefully in a controlled fashion.
Or in an
Like
orderly.
your car, if you turn it on, it's cold. It's designed to warm up and expand and contract until it gets operating. So it's part of the design of the plant.
Okay.
And the operator training is commensurate with that design.
Okay, thank you. That's a very complete answer. And a question of PG&E, I'm wondering if in hindsight, it might have been wise to buy a new stator rather than do a rebuilding of the one that was reaching the end of its lifetime. And I don't even know if that was an option, so that's my question.
I'm not going to go there.
Well, I guess I'm asking PG&E that question, not the committee, if I'm allowed to do that.
Well, Ms. Swanson, that was part of my inquiry when I was on site, knowing how difficult, this remedial process had been for the licensee. So part of my question is, why did you do what you did? Could you have done something else? Right? Yeah, but hindsight is always 20/20, right?
Not always, of course, either.
Dr. Gene Nelson, California Green Nuclear Power. And I've got some general questions for Mr. Harbor. They're engineering type questions. And I wanted to get a sense of the voltages and currents flowing through these conductors for the generator. I appreciate that this generator, this one single generator, is generating 5% of the power that's generated in California. So again, some numbers there, and perhaps also compare and contrast that. I have a small generator at my home for emergency purposes. It's rated at 5 kilowatts. So I would like to get a sense of that, and then also just a sort of a general sense of the level of forces on these conductors. I believe they're going to be, by Lenz's law, they're going to be measured in tons, but they're going to be dynamic forces. They're going to be oscillating at 60 hertz because that's what we're producing. We're producing pure 60 hertz sine wave power. So anyway, those are the questions. And also, I'll express my view as a perhaps more technically educated member of the public, but a member of the public nonetheless, that I'm also quite impressed with PG&E's response, both their caution and their working towards resolving it and having the end result of having a machine that has lower vibration. And I guess that also brings up the reminder of the other question. I recall on a public tour that in the generator hall, there was a large instrument console. I think it stood about 6 feet tall and maybe 3 feet by 3 foot. And during the tour, they mentioned that was the vibration monitoring equipment. I think it was from Brule and Kajir. And so I wanted to find out if that's where all this, where first the problem was discovered and where it's being monitored from. So those are my questions.
Mr. Harbor?
Anybody want to answer the question about the current and the voltage?
Well, I believe the questions were directed to Mr. Harper.
Yeah, sure.
Yeah, sure. I can answer the questions as much as I can here. Some of them I won't know the exact answer, but I'll start with the question on the voltage emanating from the machine. So the voltage from the machine at the locations that we saw there, it's about 25,000 volts. And then that 25,000 volts then goes to a step-up transformer to 500,000 volts, and then that goes out over the grid. So pretty significant voltage load. And then as far as the second question in terms of amps, I'll just speak to it in terms of, sort of power, megawatts, and so on. So each one of the Diablo Canyon units is about 1,150 megawatts output, roughly. And as Mr. Nelson said, Dr. Nelson said, they do supply about, equivalent of about 5% of the power for the state of California. I mean, for the PG&E territory. So a significant amount of power. So as we're going through that, that's why it was so important for us to make sure we work through this and be able to get that back so that it could supply our customers and or the state. See, the next question that was asked, I'm sorry I didn't write them down. Yes, it's where is the vibration is being monitored. So your memory serves you very, very well that there is you described it perfectly, on the turbine deck is a vibration monitoring panel for each one of the units. But that particular vibration monitoring panel pretty much monitors, for the most part, the rotating elements of the unit.
Shaft.
Exactly, it's a sort of shaft rotating. So it's monitoring the bearings of all of the the different rotating components, and it's trying to see if it's maneuvering. Now, through all of this, those vibrations of all the bearings were always well within parameters. They never went outside a parameter. So that was not so much the issue. And so the additional vibration information we put in, they were supplemented and not normally installed, which gave us more specific information about how the machine itself externally was moving.
Thank you. Any other
additional public comments on Mr. Harper's presentation?
Thank you.
Mr. Zick, any audience remarks from the Zoom?
Yes, Mr. Giesman, you can talk to the board now.
I'm connected by phone now. Can you hear me?
Yes.
This is John Giesman on behalf of the Alliance for Nuclear Responsibility. Hello, Mr. Harbour. My question to Mr. Harbour relates to vendor management or vendor relations management. And I'm wondering, I noticed both Dr. Budnitz and Mr. Wardell were quick to employ car metaphors for this situation. I'm wondering, Mr. Harbour, if you had bought a new car and had this level of difficulty with it in its first year and a half of ownership, at what point you would stop raving about the insightfulness and cutting-edge nature of your mechanic and tell the vendor, this is not the car I thought I was buying, either give me a new one or make financial redress.
John Giesman, this is Bob Budnitz. John Giesman, this is Bob Budnitz. Well, you know perfectly well that's outside our remit. But what I was praising was the response by the response people, and that's very separate from whether or not if I bought a car like that, I'd be happy about it. I might bring it to the dealer and say, gee, the repair people did a great job, but I still might be madder than the dickens at the manufacturer. I know you understand. I know you understand that distinction.
As we edge our way into more and more difficult supply situations, during the summer on California's grid, this particular unit takes on a much higher level of importance than it would otherwise. And it would seem to me that rather than sit around and congratulate ourselves on what a brilliant set of repair strategies we've come upon, we ought to focus on whether or not this was a good idea in the first place and how we get out of the situation we're currently in.
Well, but that goes to the root
I don't
cause.
hear much about it.
But that goes to the root cause analysis that is underway that we're still waiting to understand. We, our committee, and everybody else too, so that we can understand what it was. Because you can't think of remedial action sensibly till you understand that. I mean, that's what we're waiting on. Everybody, I think, here understands that.
Now, as Mr. Giesman's remark were directed to Mr. Harbor, Mr. Harbor, do you care to respond to Mr. Giesman's inquiry?
Kerry Harbor. No, not at this time. Like as you mentioned, hindsight is always 20/20. We focused on trying to alleviate the issue, repair it, and get the unit back up. And at this point in time, we continue to work through the final root cause analysis.
Okay, to
Well,
provide
let's not go into hindsight. What was your reaction when you learned of the hosing problem in this most recent incident?
Well, I think we're all in John. We're all in the same boat. We're discouraged by that, and trying to find a path forward that makes sense. I mean, by the way, your car analogy, you know perfectly well, doesn't fit. If I had a car like that, I would take it down to the dealer and ask him to give me a new one. But if you do that, the plant's down for I don't know how long while a new one comes, because it takes 3 years to get a new one. So that's not, in fact. A good analogy, and we all understand that.
Well, in a way, it is a good inquiry, but I think your response, Dr. Butner's, illuminate about why that option was not considered.
Yeah, I mean, we're in a dilemma.
Right. So, that is a good clarification. They bought the car, but returning the car will shut down the plant for 3 years. So
something like that.
Right. They don't have that option.
Now, I would be very concerned if this was a nuclear safety issue, but I've concluded that it isn't, which is our remit. So we're just trying to understand to the extent, for example, it could be a nuclear safety issue if we ascertain together that a safety culture lapse was what was the underlying thing here, and we're going to wait and see. John, I hope that helps. I think we understand each other about the dilemma we're in.
I think we do. Thank you.
Thank you, Mr. Giesman.
I would like to re-stress a point. I'm not sure if Mr. Giesman has a video feed of the slides. He may just have a telephone connection. And I want to reiterate something from the next to last slide. The last bullet point. The vibration was below the baseline and stable with the addition of supports and bracing. That suggests to me, as an engineer, that this, going back to the car analogy, this car now is even better tuned than it was prior to the repairs. And that gives me confidence as an electrical power consumer on the Central Coast that the lights will stay on because of Diablo Canyon. However, thanks to other issues in California, we may have rolling blackouts anyway. Thank you.
Thank you.
And Bob Budnitz will tell you I'm holding my breath if this thing doesn't come back. Okay?
Okay.
Can't be more candid than that.
Additional public comments?
Good evening, David Weissman, Alliance for Nuclear Responsibility. Just procedurally here, that the refrain of what part of those questions, for example, Mr. Giesman asked, are not your remit, especially the ones involving the budgeting of the process and so forth. Again, I go back to October of 2019. The question of Dr. Lamb. Now, the stator typically lasts 20 years, and you were replacing it for an expected service life duration of 4 to 5 years, which is now like 3 years. And he says, that's correct. And you say, well, that's indicative to me that budget concern doesn't apply here. And Dr. Budden says, well, without it, they couldn't make power. If it goes down, that's a whole lot of millions of dollars. So even though you say it's not your remit, the money issue does factor in to the conversations that you do have.
Of course it does.
So it can't, I don't think it can, be as glibly dismissed as like not our remit, because that's the factor of your creation of the Public Utilities Commission, which controls the economics, not the NRC. So,
of course.
Thank you.
Thank you, Mr. Weissman. Any additional public comments on Mr. Harbor's presentation? If not, let me ask Mr. Mr. Zeke, do you see a Zoom audience request?
Yes.
This is Tom Murray. Can you hear me?
Yes, Mr. Murray. Yes, we hear you.
Okay. Mr. Weissman just brought up something interesting financially. And you spoke about how just wonderful it was that the engineering team at Diablo Canyon just got on this Jiminy Cricket real fast and did a great job. Why? Is a question. Well, it might have something to do with the rep from the CPUC who was here at your last meeting, who was checking in on this to see if she was going to have enough power to power all the air conditioners in Los Angeles. Just a thought. What do you think? Do you want me to go through the litany of just who you're dealing with here in PG&E? I can. It will be very illuminating. Well, to start with, since you're silent, this is a company who not only has the power delivery company gone through bankruptcy, also the holding company has gone through bankruptcy in the last 10 years. This is a company who has admitted to killing, just shy of 90 people. We're talking about San Bruno, of course, and the Paradise Fire. And you guys are standing there or sitting there like these people are not necessarily suspect. I think they are suspect, and I think they should be watched like a hawk. And their reasons for getting on this are obvious. They are protecting their license from the CPUC, period. That is all.
Thank you for your remarks, Mr. Murray. Additional public comments? Mr. Zick? There being none, let me thank our speaker for an informative presentation and then turn the podium over to Mr. Tom Bowen. Mr. Bowen?